In 5.3, we are going to analyze the tangent function. Like y equals sine x and y equals cosine x, we are going to create a table of values for tangent using the unit circle, and then we are going to plot those points to see what the tangent function looks like. Also, like sine and cosine, the tangent function is a periodic function. That means that it is going to repeat the same y values for a specific interval of x values. Unlike sine and cosine, you'll remember from the unit circle, the sine theta came from the y values on the endpoints of the terminal arm of the unit circle. The cosine of an angle comes from the x coordinates. Well, tangent comes from taking the y values and dividing by the x values. That's where tangent of the angle theta comes from. Because that is written as a rational, that means that we have to look at some restrictions. So that's what this next question is asking. Where would the tangent function be undefined? So again, since tangent theta is equal to y over x, this is going to be undefined when x is equal to 0. Well, where is x equal to 0? We could also say it is when cosine theta is equal to 0. Well, we can look at it two ways. If we're thinking about the unit circle, x is equal to 0 when theta is equal to pi over 2 and 3 pi over 2. But we could go around the circle multiple times. So anytime we hit a pi over 2, that's going to be where tangent is undefined because x is always 0 on that vertical axis. So I can't just list it as pi over 2 and 3 pi over 2. We have to make a general statement. The general statement is theta equals pi over 2 plus pi n, where n is any integer. You'll remember that this was actually our x-intercepts for cosine, and that makes sense because this is going to be undefined where cosine is equal to 0. That means the x-intercepts. So these points are really important when it comes to tangent because this is where tangent is undefined. We also said that this looks like it's rational. So you'll remember from chapter 9 when we talked about rational functions and when we talked about the points where rational functions are undefined, we ended up having a vertical asymptote. The same thing happens here. So how would the graph of the function respond? We are going to have vertical asymptotes at those places. So vertical asymptotes at theta equals pi over 2 plus pi n, where n is any integer. Now, that means right away that the graph of y equals tangent theta is going to look much different than y equals sine theta and y equals cosine theta. They did not have any asymptotes. Their domain was x is the element of the reals. Here, our domain is limited. So tangent, while being a periodic function, is still going to look very different than sine or cosine. So here's our table of values, and we can just think a little bit about the unit circle as we go around. So we're going to start off with 0. So our coordinates when theta is equal to 0 is 1, 0. So y over x is 0 over 1, which gives us 0. At pi over 6, we're at root 3 over 2, 1 over 2. When we put y over x, that's going to end up giving us 1 over root 3. At pi over 4, we're at root 2 over 2 and root 2 over 2. So y over x is going to give us 1. At pi over 3, our coordinates are 1 over 2, root 3 over 2. Y over x is going to reduce to root 3. Now we're up here at pi over 2. And at pi over 2, we're undefined. At 2 pi over 3, we're going to get the same ratio as we would for pi over 3. But because we're in quadrant 2, it's negative. For 3 pi over 4, we're going to get the same ratio as pi over 4, which is 1, but in quadrant 2, it's going to be negative. At 5 pi over 6, we're getting the same ratio as pi over 6, but in quadrant 2, we're negative. When we continue around the unit circle, now we're in quadrant 3. So at pi, we're at 0. At pi over 6, again, same ratio as the other pi over 6's, 1 over root 3. Because we're in quadrant 3 and tangent is positive in quadrant 3, that ratio is positive. At 5 pi over 4, we're at positive 1. And at 4 pi over 3, tangent is equal to root 3. Now we're at 3 pi over 2, undefined. 5 pi over 3, same ratio as the other pi over 3's, tangent's equal to root 3. Because we're now in quadrant 4, it's negative. 7 pi over 4, our ratio is 1. Because we're in quadrant 4, our ratio is negative. And 11 pi over 6, our ratio is 1 over root 3. Negative because we're in quadrant 4 and we're back to 0. So the pattern for tangent looks different than the pattern for sine and cosine. The numbers are different. And we should also notice another big difference. We go from 0, 1 over root 3, then 1, root 3 undefined, root 3, 1, 1 over root 3, 0. So we go from positive to negative. And then look what happens here. We start at 0 again, and the pattern actually repeats again. So here is our first, this is halfway around, and then this is the other half around. And you'll notice that the pattern repeats exactly for the second half as it does for the first half. This is because tangent is positive in quadrant 1 and in quadrant negative in quadrant 2, and then positive in quadrant 3 and negative in quadrant 4. It does not take 2 pi radians to go through one complete cycle of tangent. It only takes pi radians. We only need to go halfway around the circle to get through one cycle of tangent. So that's another difference between tangent and sine and cosine. So let's take those coordinate points and let's plot them here. We were at 0, 0. We have pi over 4, 1, and we have the ones in between there. So we have the root 3 and the 1 over root 3 and the root 3. Kind of tough to graph here. At pi over 2, I'm going to dot in that vertical asymptote. At 3 pi over 4, we're at negative 1. At pi, we're at 0. 3 pi over 4, positive 1. And then there we go. We could keep going all the way around. Now, it's kind of hard to see here because we just have the dots on there. But here's what ends up happening. If we just keep continuing the pattern, this is going to go back down here to negative 1, back to 0, positive 1. Asymptote, we could work backwards here. Negative 1, asymptote. Here's what it ends up looking like. So it follows the asymptote, and then it curves till it hits here, and then it's going to curve up that asymptote. Same thing here, follows the asymptote, curves through the points and up the asymptote, and again, and it just keeps doing that over and over and over again. That is what tangent looks like. We could get a bit of a clearer picture if we graph it on our calculators. So going into y equals, and we'll put in y equals tangent x. Right now I am in radian mode, so I'm going to put the windows in radians. We'll go from negative 2 pi to 2 pi. And we'll go by a scale of pi over 4, like we have here in the notes. And now this is not bounded. So sine and cosine, we're bouncing in between 1 and negative 1. Tangent is definitely not doing that. So we don't need to worry about the y min and the y max. And there's tangent. Now, those vertical asymptotes are invisible. So my calculator is graphing those vertical asymptotes. They're invisible. All we see are the curves in between, and that is tangent. So now that we've graphed it, let's go ahead and analyze the characteristics of tangent. Our domain then is the set of all x such that x cannot equal pi over 2 plus pi n. So x does not exist where our vertical asymptotes are. Otherwise, x is an element of the reals. Our range, well, we're not bounded by 1 and -1 anymore because we have these vertical asymptotes. Our y values are taking on all possible values. So the set of y such that y is the element of the reals. The x-intercepts, we can see that it is crossing at here. It crosses at pi and then 2 pi and 3 pi and so on. So it is crossing all of the, crossing the x-axis at all the pi values. So we're going to write that as pi n, where n is an element of the integers. And you'll remember that this is the same as the x-intercepts for sine. So sine and tangent have the same x-intercepts. Our y-intercept is at 0, 0. So let's have a look at these two things down here. Comment on the following attributes of tangent x, and the first is amplitude. We talked about amplitude with sine and cosine, which was the distance between the midline and the maximum, or the midline and the minimum. Quite clearly, tangent does not have a maximum or a minimum. Its range is y is the element of the reals. And while it's a periodic function, it's not a wave function. So we would say none for the amplitude. It doesn't have one. It doesn't exist for tangent. The period, however, does, because it's repeating that same pattern over and over and over again. And we did notice that, unlike sine and cosine, it only takes halfway around the unit circle to get through one complete pattern of tangent or one complete cycle of tangent. So the period of tangent is pi, or in degrees, 180 degrees. We should also maybe go back and do that here. The domain would be x cannot equal 90 plus 180n. We could write that in degrees. And the x-intercepts are at 180n, where n is an element of the integers as well. We have one example for this section, and here's what it says. Given that the function f at x equals sine b at x has the same period as tangent x, what is the value of b? Okay, well, the period of this guy, remember to find the period is equal to 2 pi over b. We don't know what b is, so that's all we can write for the period of that function. The period of this function we just talked about, it is equal to pi. Well, if these two things are equal to each other, that means that 2 pi over b is equal to pi. And hopefully upon inspection, we can just see that means b is equal to 2. We will not do any applications with tangent. We will not do any transformations with tangent. All we need to know for tangent is the shape of the graph, the characteristics of the graph, and you should have an understanding of why tangent looks the way it looks. Why are there asymptotes? Why is the period pi?